All right, and we are back getting ready to talk about exercise 1.5, which is on polynomials, in particular cubic polynomials. So, as a quick refresher of exactly what a polynomial is essentially a series of, so it's an expression that contains the sum of a bunch of variables that have non-negative integer powers. So, for example, if we have x to the power of 2, 2 is a whole number. That's a polynomial. If we have 3x to the power of 3, polynomial, 2. So this is actually x to the power of 0. So that's a polynomial as well. If we just had y equals 2, technically that's a polynomial of degree 0, because we could imagine there's x to the power of 0 here. Anything to the power of 0 is 1. But as soon as we have something like this, 1 over x, although we could write 1 over x as x to the power of negative 1 is a negative number, therefore this is not a polynomial. So polynomials, they need to have whole number powers associated with their each of their variables. Okay. If we have a polynomial written like this, for example, x cubed plus x to the power of 4, we define the polynomial based on the highest power that is contained. So the highest variable power is 4, so we would define this as a quartic polynomial, which is to say a polynomial of degree 4. If we didn't have that power of 4 there, we would have a cubic polynomial. This is an expression. Right now, we can make it an equation by putting in an equal sign. As soon as we have an equal sign, it becomes a cubic. So it becomes an equation. So that's how we do this. All right, so there's a few important theorems that you need to be aware of when it comes to polynomials. The first one is the remainder theorem. So the remainder theorem states that if a polynomial is divided by x minus a, so we're going to take the polynomial, we're going to divide it by x minus a, which is what we do when we factorize. We take out the common factor of x minus a, put it out the front, and we write what's left over when we divide that. We're going to get a remainder of p of a. So when we do this, the remainder of that, is equal to p of a. So all we have to do is substitute a into the polynomial, and we can figure out what the value should be. So let me just come up with a polynomial. We're going to write this one down. We'll use this in a minute as well. We have, okay, this one here. So 2x squared minus 5x minus 2. We're going to call this p of x. Now, if we have a look at this theorem here, the remainder theorem, it basically says that if we were to divide this, if we wanted to know what was this polynomial equal to when we divided it by, let's say, x minus 1. So let's write out what we want to do here. I'll just get rid of all this. What we want to do is we want to divide this by, so we want to go p of x divided by x minus 1, okay? To do this, that will be equal to, so the remainder of that will be equal to p of 1. So I'm going to take 1 and I'm going to replace the x values in this formula with 1. So we're going to get 2 times 1 squared minus 5 times 1 minus 2. Now that's going to be equal to 2 minus 5 minus 2. Let's say that this is 3. I think it'll work out nicer later down the track. So let's say that's 3. Okay, so we have 3 minus 5 minus 2. Now, minus 5 minus 2, that's equal to minus 7. 3 here, so that's going to be equal to minus 4. So essentially what this is saying is when we divide a polynomial by x minus 1, we get out an answer of negative 4. Now, the factor theorem then says if, a polynomial only has a factor of x minus a if and only if p of a is equal to 0. This is a direct consequence of the remainder theorem. The only way that a linear binomial is going to be a factor of a polynomial is if when we perform this division, we get a remainder of 0. So as we can see here, based on the factor theorem, what we've just done here tells us that x minus 1 is not a factor of p of x, because when we divide it, we get an answer of -4, not 0. So how do we figure out what the roots or the x-intercepts of a polynomial actually are? Well, we have to use what's called the rational root theorem. So the rational root theorem states that a polynomial px is equal to 0 will have solutions, also known as roots, also known as x-intercepts. They all mean the same thing. It will have solutions of the form x is equal to p over q, where p is a factor of the constant. So look over here. The constant is this number right here, okay? So p is a factor of the constant, and q is a factor of the leading coefficient. So if you look at this example over here, the leading coefficient is 3, okay? So basically what this is saying is the numbers that we're going to try for our factors need to be of that form. So why don't we just quickly consider what are the possible factors of 3, for example. So the leading coefficient 3. This could be plus or minus 1 or plus or minus 3, because we could have, so these are the only possibilities. Because 3 is a prime number, they're the only possibilities. In the same way, we could consider factors of -2. So that's the constant term, -2. The factors of -2 are plus or minus 1 or plus or minus 2. And again, 2 is a prime number, so these are the only possibilities. That's why I've chosen this one over here. Okay, so looking at this, what we can see here is that this polynomial, so a polynomial of degree 2, it's called a quadratic, but it's still a polynomial. This polynomial, if it has rational solutions, and there is no guarantee that it will have rational solutions, because we know to find the x-intercepts of a quadratic, all we need is actually to use the formula plus or minus b squared minus 4ac. So negative b plus or minus the square root of b squared minus 4ac over 2a. Notice the presence of this square root term. We could actually end up with an irrational number if this comes out to be a surd. In which case we won't have rational solutions. So the rational root theorem is just predicting if rational solutions do exist for this polynomial, they will be of the form of one of those numbers in green divided by one of those numbers in orange. So we've already tried 1. That would be 1 divided by 1. Why don't we try a different one? So maybe we can try -1. So if we put in -1 into this equation, so let's try -1. Is -1 a factor? If this is equal to 0, it is. So we'll go 3 of -1 squared minus 5 of -1 minus 2. Okay, well, -1 squared, that's just equal to 1. So this is 3. Double negative, that makes plus 5 minus 2. So this is now 8 minus 2. That's equal to 6. That is not equal to 0. Okay, well, that tells us, what does that tell us? Well, that tells us that -1 is not a factor of this particular polynomial. Right, so I guess it's back to the drawing board on that one. So why don't we now try, let's do it over here so it's a bit easier to see. Why don't we try, let's say, one of these green numbers. So it could be 2 divided by 1. So is 2 a factor of this polynomial? So let's put in 2 over here into this equation. So that will mean that this equation will become 3 times 2 squared minus 5 times 2 minus 2. All right. So 2 squared is equal to 4, so that becomes 12 minus 10 minus 2. So that's going to be 12 minus 10 minus 2. That's equal to 0. So what does that tell us? Well, that tells us that x minus 2 is a factor. Why is it x minus 2 and not x plus 2? Well, if we put x equals 2 into this equation, we get 2 minus 2, which is equal to 0. And if you remember, we have this thing called the null factor law. When we write a polynomial as in its factorized form, the only way that that polynomial can be equal to 0 is if one of its linear factors are equal to 0. So x minus 2 is a factor because if I put in 2 into this equation, I'll get out 2 minus 2, which is 0. If I put in 2 into the expanded form, I also get out 0. Makes sense because they're equal to each other. Okay, so we now know 2 is a factor, or we could say that x minus 2 is a factor. They're kind of the same thing as each other. All right, now here's a couple of quick definitions. We should be quite comfortable with these already. The degree of a polynomial is the highest power of the variable. Okay, so if we look at this one here, it doesn't matter the fact that the x cubed term is seconds in this little sum here, because it's the highest power, it is a cubic. The leading term is called the term with the highest variable power. So notice the fact that in this expression, you might say that the leading term's x squared because it's the one that was written first, but it doesn't matter which way we add up. We say that addition is commutative because a plus b is the same as b plus a. So this is kind of arbitrary, but the way that we define the leading term is just the term with the highest power. So in the case of this little equation that you can see here, highest power is 3, so this is a cubic, and the leading term is x to the power of 3. The constant term is just the term that does not contain a variable, so if there was a +1 on the end here or a -1 on the end here, the constant term is -1. And we also say that a polynomial is monic if its leading coefficient is 1. So for example, if we have x to the power of 3 plus 4x, this is a monic cubic. But if we have 4 in front of the x, so 4x cubed, this is now not monic. Okay, so that's the definition of monic. All right, so now let's talk about division of polynomials. And this is a pretty important concept to understand. So division of polynomials, the way this works is when we divide a polynomial by its divisor, so we're trying to work out if something's a factor or not, the number at the top, we call that the dividend, number down the bottom is the divisor. If there is no remainder, we won't have this annoying little bit at the end here, we'll just have the quotient. But yeah, if it's not a factor, the way that we would write the answer is we would write dividend divided by divisor is equal to quotient, which is to say the whole number that the dividend divides into with no remainder, plus the remainder divided by the divisor. So let's have a quick example of that. Here we have division that we want to do by hands. So without using long division, we can try this. So the trick for this is to try and write the thing up the top in the numerator as some constant product of the thing down the bottom. So ideally what I want to put up the top is x plus 2 divided by x plus 2, right? And then we're going to have some remainder. So we can see that there's a 3x out the front here. So let's say we write this as 3x plus 2. This is the same as 3x plus 6, right? So how can I say that this is equal to this? Well, we need to account for this -4 here. We can use the fact that 6 minus 10 is equal to -4. So that tells us that this expression over here is in fact the same as this, and let's extend this, plus, minus 10, because if we expand these brackets, we get 3x plus 6, and 6 minus 10 is equal to -4. So this will be the same as what we have over there. All right, so now that we've got that, we can see that this expression is the same as that expression. That's going to help us out quite a lot, because now all we have to do is we can simplify this down. So we can just express this as, we can split up a fraction. If you remember how to deal with fraction addition and subtraction, we can sort of do it in reverse. We could write this as a difference of two fractions that have the same denominator. So we could say that this is equal to 3 of x plus 2 divided by x plus 2. And I'll just get rid of this part over here. Minus 10 over x plus 2. And now we're going to notice a very useful thing happens. We have an x plus 2 up the top and x plus 2 down the bottom. So binomial factor that's up the top and down the bottom, they cancel out because x plus 2 divided by x plus 2 is going to be equal to 1, so long as x is not equal to 0. Sorry, so long as x is not equal to 2, because then down the bottom we'd have -2. Then we'd have -2 plus 2, which is equal to 0. So x cannot be equal to -2. But aside from that case, this will always cancel out. Then what we can see here is that we have successfully written this as this form. So we have dividend divided by divisor is equal to a quotient plus a remainder divided by the divisor. So in this case, we can see that the remainder is negative 10. So another way that you could do this exact same division is using polynomial long division. Now, the way polynomial long division works is we basically put the dividends underneath here, so 3x minus 4, and we put the divisor out here. So this is x plus 2. And what we do is we take the leading term of the dividend, divide it by the leading term of the divisor. So 3x divided by 3 is equal to 3. And then we put it over here. So it's in the same, in line with the same type of variable. So this is constants over here. So 3x divided by x is equal to 3. And then we take that term, we multiply it by the numbers out in the divisor here. So 3 multiplied by x is equal to 3x. 3 multiplied by 6 by 2 is equal to 6. So 3 times 2 is 6. 3 times 1 is 3. Then we take these terms here. We subtract off these terms here. We have 3x minus 4 minus 3x plus 6. 3x minus 3 is going to be equal to 0. So 3x minus 3x. And minus 4 minus 6 is equal to minus 10. As we can see, this down here is the remainder. That's the remainder there. So we can see that when we divide this value by this, we get 3 with 10 remainder, which is exactly what we got here using the other method that I showed you before, the inspection method. So that's two ways that we could perform this. Long division is also very useful, as you well know, when it comes to factorizing cubics. So let's suppose we want to divide this equation here, or this expression here, by x plus 3. How do we do that? Well, it's basically exactly the same as what I just showed you there. Well, I'll show you with long division and with synthetic division. Synthetic division being considerably easier. So let's just write it out. We put the dividends down here. So the dividend is the number up the top of the division. So that's 4x cubed plus 6x squared minus 5x plus 9. Out the front here, I put the divisor, so x plus 3. And then we do exactly what I just did before. We take the leading term of the divisor, divide it by the leading term of the dividends, of the divisor, sorry. So the leading term of the dividend divided by leading term of divisor. So 4x cubed divided by x is equal to 4x squared. And then we go take that number, multiply it by the numbers at the front. So we have 4x squared times x, which is equal to 4x cubed, 4x squared times 3, which is equal to 12x squared. We take that number, so take these two terms minus from these two terms. So 4x cubed minus 4x cubed is equal to 0. And then we have 6x squared minus 12x squared, which is equal to minus 6x squared. Next thing we do is we drop down the next term. So we're going to drop down this term here. So the negative 5x, that comes down here. Negative 5x, and now we're just going to do the exact same thing. So this time we're going to take the leading term of the dividends divided by the leading term of the divisor. So we're going to take minus 6x squared divided by x. So this is going to come out as minus 6x. Take this, multiply it by this. Negative 6x times x is equal to negative 6x squared. Negative 6x times 3 is going to be equal to negative 18x. That minus that is 0. Then we have minus minus 5 minus negative 18. So that's going to be plus 18, which will come out as 13x, because minus 5 plus 18 is equal to 13. Take that, put it up here. So that's going to be 13x divided by x. And then we can see that that will be, we get that term, we multiply it by the numbers out here. Also, we need to drop down this 9, don't we? So this is going to be plus 9 down here. Go 13 times x, which is 13x. 13 times 3, which is 39. This minus this, that's 0. 9 minus 39 is equal to 30. Therefore, the answer, when we take this number divided by this number, is what we have written up here, 4x squared minus 6x plus 13, with the remainder of negative 30. So that there is the remainder. And we could then write it in the form, just like we did before. We could say that it's equal to this, the quotient, plus the remainder, so negative 30 divided by the divisor, x plus 3. Now, a quicker way of doing a question like this is using synthetic division, which is a really good method that you should be aware of. So let me show you to you really quickly, how do we do this faster? So very useful when it comes to exams. What we can do is we put the factor out the front here, but we write it as the actual number factor. So when is this equal to 0? Well, it's equal to 0 when x equals minus 3, because minus 3 plus 3 is equal to 0. We write that out the front here. We have like a weird line thing like this. I don't know what you call it. And then we just take each of the terms, so each of the coefficients of these terms in descending order. So first up 4, then 6, then minus 5, 9. By the way, if, for example, we didn't have an x term here, it was just 4x cubed plus 6x squared plus 9, then we would have to leave 0 in this place here. So this would be 0 if there was no minus 5 here. So we need to include all of the terms counting down. The method essentially works where we just take this number here, we drop it straight down. So we drop down the 4. So we put 4 here, and then we go minus 3 times 4. So minus 3 times 4 is equal to negative 12. And I go 6 plus negative 12, which is equal to negative 6. Then I go negative 3 times 6, which is equal to, sorry, times negative 6, which is equal to positive 18. Then I go minus 5 plus 18, which is equal to 13. Then we're going to go negative 3 times 13, which is equal to 39. Running out of space over here. And then finally we have, sorry, that should be minus, shouldn't it? Because we had negative 3 times 13, so that's a negative number. So negative 39, and then we're going to go 9 plus negative 39, which is equal to minus 30. That is our remainder, minus 30. This is the remainder, and it's hard to see. The remainder is minus 30, and you can see that these terms here are the same ones that we had up here. So the coefficients of the divisor that we found up the top here. So therefore, the answer is going to be equal to, well, it's going to be equal to 4x squared plus 6x minus 5. So it should be 4x squared minus 6x plus 13. So I read these numbers down here as the coefficients with our remainder of negative 30 over x plus 3. So that would be the answer that we'd get here. All right, so that's how we do that. Now, how do we use this when we factorize? Well, few notes on factorization. The first thing you should do when trying to factorize a cubic is to look for some kind of pattern so that you don't have to do these kind of procedures. It'll just save you a bit of time. So the patterns you're looking out for is perfect, not squares, perfect cubes. Perfect cubes look like this. So we could have a plus b cubed is equal to what you can see here. Sum of two cubes, which is where we have a cubed plus b cubed, or difference of two cubes, a cubed minus b cubed. They factorize like so. So let's see if we can apply one of those here. So first thing we should notice, whenever we see numbers like 8, 27, 4, we're looking for cube or square numbers. So let's go ahead and see if we can factorize this. Well, we can see that this is the same as x cubed plus 2 to the power of 3. And now we can see that that is actually in the form of a perfect cube, which is what we have here. Sorry, not a perfect cube, it's a sum of two cubes, isn't it? So it's the one that looks like this, a cubed plus b cubed. So therefore we can factorize this as x plus 2, because a is equal to x, b is equal to 2, times x squared minus 2 times x plus 2 squared, or 4. and then we could then see if we can factorize that any further. So that would be how we'd factorize one of these. So then what we'd be looking for is we'd look at this x cubed minus 2x plus 4. Can we factorize that any further? It's not immediately obvious. What about the fact, well, do two numbers add to give -2 multiply to give 4? So the factors are 4, that could be 1, 3, 2, and 2, and if we considered negative and positive versions of those, I don't think any of them are going to work here. So it's possible this might have irrational solutions. But anyway, this is how we start factorizing one of these guys. In fact, you should know how to do this in the CAS calculator. So can we factorize this any further? Let's just have a look. So we have factor x cubed plus 8. That is in fact as simple as we can go. So that must mean that if we look at this one here, if we look at this quadratic, if we were to try and find the discriminant, the discriminant is going to be equal to b squared minus 4ac. B squared is minus 2 squared minus 4 times 1. That's going to be equal to 4 minus 16. That's going to be a negative number, less than 0. So therefore, this has no solution. So therefore, we can't factorize any further. So I probably should have started with that. All right, let's move on to the next one. So can we look for any patterns in this one here? So it's not immediately obvious with a question like this, but again, let's just see if we can just simplify this. I see 27s and 9s. They're all powers of 3. So why don't we just simplify this and write this as 3 cubed y cubed minus 3 cubed y2 plus 3 squared y minus 1. Just because we know 27 and 9 are powers of 3, we know we can do that. So can we look at this? Can we see any of these patterns up here? It kind of looks a little bit like a perfect cube. So can we write it in the form a cubed plus 3a squared, so b plus 3ab squared plus b cubed? Let's give it a crack. So let's suppose a is this term here. So could we write it where this is a? Okay, well, in that case, then our a term would be 3y cubed. Then we'd have, so we need to have a, well, let's say plus 3, because we're trying to get into this form. There needs to be a 3 out the front. We should have a squared. So a squared was 3y squared. Because 3, sorry, there should be a bracket there. So 3y squared, because 3 squared, that's 9, and 9 times 3 is going to be equal to 3 cubed, and I think that needs to be negative. How about if, yeah, let's consider, okay, so 3y squared, and then we've got this pesky minus 1 out the front here. So how could we possibly end up with a minus 1 out the front? Well, possibly, we know that the final term needs to be b squared. Maybe the final term is -1, and then we know -1 cubed is -1 times -1 times -1, which is a negative number. So it's possible that that could be our -1. So let's say this is -1 here, then we're going to end up with a -3 there. Then we're going to have over here, so we need a 3, and then we have 3y to the power of 1 times -1 to the power of 2, plus -1 cubed. So written in this form, you might see that that is a perfect cube. It's kind of hard to see when you're not used to this kind of pattern. You might have to use polynomial long division or just like, rational root theorem, see if you can find the answers that way. But we can see here possibly that this here is in fact a perfect cube of this form. So therefore, this can be factorized as 3y minus 1 cubed, because the a term in this equation here is 3y, and the b term is minus 1. All right, so another factorization technique that you should be aware of, we can see if we can factorize by grouping. So here's a couple of quick examples on how to factorize by grouping. So this one here, again, it's not immediately obvious. What are we supposed to do here? Well, what we could see is that we have some m's and we have some n's. So first up, let's just write this slightly differently. I want to write it as, well, ideally, we can see there's quadratic sort of relationship with these n's. There's only one m, there's two n's, and then this is a constant. We can include that in whatever we like. So why don't we take out the minus sign and let's write this as n squared plus 12n. I'm going to write in descending powers of n plus 36. So writing it like this, you should be able to see that these two things are the same as each other. We can now see that this is just simply a monic quadratic. So can we think of two numbers that add to give 12 and multiply to give 36? Well, 36 is 6 times 6, and 12 is 6 plus 6. So this is actually a perfect square, which means we can write this as m squared minus n plus 6 squared. So we factorize that part, and now we look at this, and this is now actually a difference of two squares. So we can factorize this as m plus n plus 6 times m minus n plus 6. And that would be the answer fully factorized. That method that I just showed you there, that's called factorizing 3 and 1. This one here is factorizing by grouping 2 and 2. So if we consider this, okay, again, you could just go straight to the rational root theorem, see if you can find some solutions. But if we want to do, so this one here, like I said, this is 3 and 1. This is going to be 2 and 2. Let's consider the first half of this. So can we see any common factors for the first half of this cubic? So we can just do it quickly. So let's consider this half here. Well, the common factor that I can see, let's leave it that color. Common factor that I can see here, I can see p squared as a common factor. So let's take out p squared. That leaves behind p plus 2. When I divide, p cubed divided by p2, that's equal to p. 2p squared divided by p squared, that's equal to 2. All right, and for the second two terms, let's have a look at that. So I want to factorize the second two terms. So notice the minus 4 comes with this term here. So I'm going to consider these two terms. We're going to take out common factor of minus 4, because we can see that both minus 4p and minus 8 divide by minus 4. Take that out, we're left with p plus 2, because minus 8 divided by minus 4 is equal to plus 2. Okay, so now as we can see, we have a common binomial factor, which is very convenient because then we can factor out that common binomial factor, right? This is p plus 2 times p squared minus 4. These are just a couple of very useful tricks that I would recommend having up your sleeve. Okay, but always we need to know how to do polynomial long division. So let's suppose we can't find any quick, easy tricks. We can't figure out how to factorize something. Maybe you can come up with an alternative way of doing this one. I'm not sure. But let's just quickly see if we can factorize this using one of our methods just to put it all together. So let's first call this here p of x is equal to this. And let's try our rational root theorem. So by rational root theorem, the factors, so the possible factors of this equation here could be, could be factors of this divided by factors of this. So factors of 3, we could have 1 over 1, so just plus or minus 1. We could have 1 over 2, so plus or minus 1 over 2. We could have plus or minus 3 over 1, which would just be plus or minus 3, or we could have plus or minus 3 over 2, so plus or minus 3 over 2. And these are the values that we would try out. So let's start by trying out, say, for argument's sake, p of 1. Let's put that into this equation. So replacing x with 1, this is going to be 2 times 1 cubed minus 3 times 1 squared minus 8 times 1 minus 3. All right. So 2 times 1 squared, that's equal to 2, minus 3 times 1, minus 8, minus 3, that is definitely not equal to 0. Okay, let's go back to the drawing board on that one. Why don't we try minus 1 here? So let's try a p of minus 1. substitute in -1 to each of these expressions. Okay, so 2 times -1 cubed. So -1 cubed is equal to actually -1. So that's going to be -2 there. Then we have -3 times -1 squared. So that's going to be positive, which makes this negative here. Then we have -8 times -1, which comes out as +8. And then over here, we have -3 at the end there. Now, collecting all this together, we can see -2 minus 3, that is -5, plus 8 is 3, minus 3 is 0. So therefore, -1 is a factor. Okay, let's now apply synthetic division, for example, because it's much faster. So let's do what we just practiced before. We put in -1 out the front here. And I'm just going to write in each of these terms here, so each of the coefficients of the terms. So I'm going to write in 2, -3, -8, -3. And I'm going to drop down. I'm going to drop down the 2 straight away. 2 goes down the bottom, and now we start. We take the number out the front here, so the factor that we found, -1 times -2, that's equal to -2, and then I add up these. I've got -3 plus -2, that's equal to -5. Then I go -1 times -5, that's equal to +5. Then we have -8 plus 5, which is equal to -3. Then I go -1 times -3, that's equal to 3. -3 plus 3 is equal to 0. So the remainder is 0. That's what we want. That is a good thing. Good news for us. It means that we did everything correctly. So therefore, we can conclude that p of x is in fact equal to, we can take out this factor, so we can take out x plus 1. When we take out that factor, we're left with the rest of this. So these represent the coefficients of the variables of this cubic. So these ones here, these represent the polynomial, the coefficients of the quadratic that we end up with. So that's equal to 2x squared minus 5x minus 3. Okay, so we have factorized that part there. All right, now let's now consider this quadratic here. So let's put all this together, see if we can revise how to fully factorize something like this. Well, this here is a non-monic quadratic, so let's use my little method before. I go 2 times -3, that is equal to -6. Can we find two numbers that add to give -5 times to give -6? So let's leave the x plus 1 out the front here. Okay, two numbers that, okay, well, what are the factors of -6? Could be, say, -2 and -3. Sorry, -2, does that work? -2 and -3. No, they wouldn't work. So what about something else? We could have, how about +6 and -1? That's almost right. That's going to be 5. What about -6 and +1? -6 plus 1, that equals -5. And also they multiply to give -6. So that's a good answer. So therefore, we can find that this is going to be equal to 2x squared minus 6x plus x minus 3. Okay, so we've just factorized, we've split that central term. This is something we did in exercise 1.5, and now we can factorize the two halves of this. So we still have the x plus 1 there. Looking at the first half here, we can take out a common factor of 2x, isn't it? So we take out 2x. That leaves behind x minus 3. And over here, we have x minus 3. And if we finally factorize that little expression there, oh, let me see, it might have just crashed on me, unfortunately. I'm so close to the end. Okay, there we go, it restored. Okay, we can finish that one up. Oh, I was close. Anyway, hopefully you can finish that one up for yourself. I'm sorry that it crashed there. Okay, so yeah, you would just factorize that and you just write it in the end as its product, as its fully factorized quadratic. So maybe you can finish that as an exercise for yourself. All right, so let's now consider this little graph down here. So last question is basically one of these sorts of questions where we need to determine the equation of a graph. So how do we go about answering a question like this? Well, we can see this is a cubic. It has two types of linear factors that we can see here. So if we recall, and Miss Martin sent out a very useful little worksheet I gave you guys in class the other day. We have the different types of factors. We have linear factors and quadratic factors. So linear factors touch and go through, quadratic factors touch and turn. So we can see here based on this diagram that we have a linear factor at minus 0.75. So therefore we can see that f of x, it must be equal to x plus 0.75. This is a linear factor. And we can see that over here we have a touch and turn type factor. So that's a quadratic factor, which means that we must have x minus 2 squared as a factor for this equation. Okay, so therefore all that remains is for us to figure out, because it's possible that there could be some constant out the front here, we need to figure out what that constant could be. The constant isn't going to affect whether or not, if I put in negative 0.75 into this equation here, I'll get 0 regardless of what a is equal to. And if I put in 2 into this equation here, I'll get 0 regardless of what a is equal to. So how do we find what a is equal to? So we're going to use the other piece of information we've been given. So we've also been given, in addition to these two x-intercepts, we've also been given this value here. So we've been given 0, negative 0.5 as the y-intercept. So we're going to use that. So let's sub in 0, negative 0.5. Remember, this is an ordered pair. We have x, then y. So we're going to sub in f of 0 should be equal to, so if I replace this with 0 plus 0.75, 0 minus 2 squared, that should be equal to negative 0.5. So let's see what a must be equal to in that situation. So if we look at this, this is going to be a times 0.75 times minus 2 squared, which is 4. And if we write this as a fraction, 0.75 is 3 over 4 times 4 is equal to negative 0.5, which maybe we'll write that as a half, so negative a half. Therefore, we can see that these two values, so the 4's are going to cancel out. And we're just going to be left with 3a is equal to minus a half. So therefore, a is equal to, well, we can divide both sides by 3. A is going to be equal to negative 1/6. And therefore, we can conclude that in the end, let's use blue for the answer. In the end, we have successfully found that f of x is equal to negative 1/6 x plus 0.75 times x minus 2 squared. And that's the answer. All right, thanks very much for joining me, and I will see you guys in the next one. Catch ya.